Hello classmates, today we will continue to study the single parameter AC circuits, load characteristics and functions. Last class, we learned about how pure resistance elements pass through a single parameter, and the characteristics and functions of sinusoidal alternating current. Today we will study pure inductance elements and their relationships with a single parameter in sinusoidal alternating currents. In our daily lives or studies, what are some common examples of inductors? For example, the coils of transformers and motors, as well as rectifiers for fluorescent lamps, are all inductive coils. If the resistance value of this inductive coil is very small, it can be negligible. And the coil can be approximately as a pure inductance coil. As the shape of pure inductance coil element, it is shown in the following figure. An inductive element is a device that can store magnetic field energy. It is the actual inductor, representing an idealized model. Its circuit symbol is shown in the left figure. The voltage only exists across the inductor when there is a change in current on the inductor. In that associated reference direction, the voltage across the inductor is related to the current as follows. The voltage U is equal to the product of the inductance, self-inductance L, and the rate of change of current. The physical meaning of this expression is that the magnitude of the voltage across the inductor is proportional to the rate of change of the magnitude of the current flowing through the inductor. When the current is DC, which means the current change rate is zero, the voltage U is zero. Therefore, in a DC circuit, the inductance is equivalent to a short circuit. When an alternating current I passes through an inductance coil, as shown on the left, self-induced, a electromotive force EL is generated in the coil. Let the current expression be I equals Im sine omega t. Then the induced electromotive force is EL equals minus L di over dt equals Em sine of omega t minus pi over 2. The voltage across the inductor is expressed as U equals minus E equals minus Em sine of omega t minus pi over 2 equals Um sine of omega t at pi over 2. Formula Em equals equals omega Lim, comparing the relationship between the voltage across the inductor and the current flowing through it. It can be seen that the voltage and current across the inductor are also sine waves with the same frequency. But the voltage leads the current by 90 degrees, or half pi, or the phase of the current on the inductor lags behind the voltage by 90 degrees, or half pi. The waveform diagram of voltage and current is shown in the figure. The relationship between the voltage across the inductor and the current can also be represented using phasors, namely Maxim phasor. The Maxim voltage phasor is equal to J omega L times the maximum current phasor. In similar manner, the effective value phasor equals J omega L times the effective current phasor for an inductance element. The voltage and current phasor diagram of an inductance element can be expressed as shown in the figure. It can be represented by the phasor of voltage across the inductor, leading the current by 90 degrees, or inductively, with the current phasor lagging voltage by 90 degrees. Let x sub L equals omega L equals 2 pi FL. Then the effective value phasor relation. The effective voltage phasor is equal to J x sub L times the current Rm's phasor. Here, XL is called inductance reactance, also known as inductive reactance, with the unit ohm. Inductance XL represents the ability of inductance to hinder AC current, similar to the resistance R of the resistive element. However, XL differs from resistance as XR is not only related to inductive components, self-inductance, L itself, but is also related to the angular frequency omega of sinusoidal current. The bigger the omega, the larger the inductance. For DC circuits, omega equals 0, XL equals 0. Inductance can be regarded as short circuit. Next, let's learn about some power-related knowledge of inductive components. The instantaneous power of inductive element is given by PL equals UI equals UM cosine omega t times IM sine omega t equals UI sine 2 omega t. The instantaneous power waveform diagram of inductance is also shown on the left. In the first and third, 1/4 cycle, the inductive element is in a power receiving state. It gets electricity from the power supply and converts it into magnetic field energy. The power is positive. Inductive element. The stored magnetic field energy of the inductive element increases from 0 to the maximum value. As the absolute value of the current increases from 0 to the maximum value Im, the magnetic field is established and gradually strengthened as the magnetic field energy increases from 0 to the maximum value. In the second and fourth quarter circles, the inductive element is in a power supply state. It converts magnetic field energy into electrical energy and returns it to the circuit. The power is negative. The current decreases from the maximum value to 0. The magnetic field disappears, and the magnetic field energy becomes 0. From the instantaneous power of the inductive element, we can calculate its average value as PL equals integrating instantaneous power with respect to time t within one single period, and then dividing it by the period. The average power is obtained by taking the average by calculation. The average power on the inductor is 0. Thus, it can be seen that inductive elements do not consume energy. they only exchange energy. With the power supply, inductor is an energy storage element. It stores magnetic field energy. Inductive element, the scale of energy exchange with the power supply, is represented by the maximum value I of instantaneous power, also known as the reactive power. Specific knowledge of reactive power will be covered in subsequent chapters. This lesson begins with the inductive element and focuses on the single parameter sinusoidal alternating current circuit. We learned about the voltage across that resistance element, the magnitude and phase relationship between currents, and the concept of inductive reactance. Inductance has a certain resistance to current, like the resistance element. We then studied the power on the inductive element from the instantaneous power waveform. We can see that the inductor is an energy storage element and does not consume energy. Instead, it carries out mutual conversion of energy with the power supply, which is described by reactive power. Classmates, this concludes the lesson. See you in the next class.